I gave you small problem to work out last time. So we will start on that. So I think I asked you to derive this derivative rule for general rule for the biases. We worked out for the weights and then I requested you to do for the biases. So has anybody done this? Anybody has tried to do this? What would be the general rule for the bias or derivative? Okay, nobody? Avinab, have you done? Try to do this? Aditi?
Sir,
Yeah.
sir, am I audible?
Yes, you are audible.
I don't know if it's correct, but I think it's
Yeah, of
n
course. We need to try. Its correctness we can verify later on. So
n
yeah.
of n of L minus 1 into delta I of L,
What is that?
like d by L.
Hmm.
Will be n of L minus 1 into delta I of L.
What n of?
L minus 1, like previous layer, whatever neuron, like where points were there, they'll all be connected to this particular neuron, right? So if we
Yeah.
change
Let me
bias in
see the
any,
expression for this. What would be the expression for this one?
which one, sir? Like d
Del
by
E del
L will
E
be,
L I.
yes, sir, it will be n of L minus 1, n of previous layer, number of neurons in the previous layer.
How are you getting n of L minus 1?
So like the number of neurons in the previous layer will be connected to this particular node, right? Which has
Huh.
the bias. So if we change bias by some value, all those n values input will change, right?
Okay.
That's how I got that n of L minus 1 factor. And then into delta L of I.
No, I don't think that is correct. So did you try to take a look into the derivation of daily del W's? I mean, it's very
Yes, sir.
straightforward, just simple modification to the previous formula that you worked out. Okay, I mean, if you take a look
Please
at
say the
this,
answer, sir. I'll check my mistake.
yeah, you can check it. I think that's not correct. Okay, anybody else who has done this? Mayank? Okay, so what I will do, I request you to work it out now. So I'll be asking questions one by one. Please do it right now. It's very straightforward from the previous derivation. Okay, so please do it. I think I'm giving you 5 minutes. Please do it, and then we will see. I mean, who were able to do it.
Sir, will it be del L plus 1I?
Say again. I mean, I just need the complete expression. Okay. So del E del Okay, go ahead. What is that?
Del L plus 1I.
Del. This is L, right? And then what?
Del L plus 1I.
Del L plus 1I. So you were saying this and then I, right? That's what you were saying?
Yes, sir.
Sir, I think it will be del Li.
Yeah, it would be del Li. That's correct. Because the BLI is associated with the neuron, lth layer neuron, ith neuron. So it would be Li. Yes, that's absolutely correct.
Yes, sir.
Right? So it is actually Li.
Yes, sir, and for del Li, we had derived the general expression in last one.
Yeah, so this is this. Okay, yeah. And then what about del Li?
So we had derived it in last class, the general expression.
Can you recall that again once more?
It is
F dash
f dash
into
of
ILI. F dash of ILI.
F dash of
ILI.
ILI and then
Summation of J varies J from 1 to NL plus 1.
NL plus 1
Delta L plus 1J.
delta L plus 1J then
Into WIJ. WL of IJ.
W L
L
of
IJ.
IJ. Okay, is anybody contesting this? Do you see any problem with this? Anywhere, any problem? So essentially the delta is the same delta that we had for weights. Okay, so there is no change, you just copying that. And only part is basically delta Li, that's it. Because the other part basically when you are computing partial derivative with respect to the input input of this with respect to biases, then it becomes 1, the factor becomes 1, so only delta I is there, is written. Okay. All right, so yeah, I believe this is correct. So in case you find any issue with this one, you let me know. Okay, now that's all right. So that's fine. Okay, now let's try to work out this simple quiz problem. And this is actual problem where you basically apply the backpropagation just to make sure that you understood things. So let me just tell you the example here. So you have this network, and on the right side you can see the small data set, the real data set, for example. Okay, so we have this ID, first column is ID, we ignore that. So there are two features, x1 and x2, and then you have the level on the extreme right, 0 or 1 level. And for this, for example, I have this network. Okay, and I have to train to figure out these parameters. Okay, see good values of these parameters. So I need to, in this example, you compute del E del W311 for sample number 1 only. For example, you are running mini batch gradient descent only with batch size 1. Okay, so for first example, you compute this derivative. And for that, of course, you need to initial values. You need to have the initial values of these parameters. So set all biases to 0. And for the weights, this is the rule. So like, when I and j equals, they basically is 1, they are 1, and otherwise it is 0. So with this initialization, with say for example the sample ID, first sample, you have to compute del E del 311. This is very simple small example, just to make sure that you understood how backpropagation is working. Okay, let me ask you this question first, and then you can proceed. Okay, now in order to do that, what's the first step I need to perform? Let's try to do it algorithmically. Okay, so what was the first step I need to perform?
So we would need to initialize the weights.
Yeah, weights are already there. You initialized. So like this, I mentioned, initial weights you have. Okay, next what you want to
Sir,
do?
we will multiply the x1 and x2 with the respective weights to find the value of activation.
Yeah. All the way to Z.
Yes.
Right?
Yes, sir.
So that's called forward pass. So you compute first that, what will the value of Z? Because you have to compute all the activations actually.
Sir, what is F? Is there any F?
Oh, right, that's right. Okay, if you can take the ReLU activation function.
Sir, will the value of Z be 2?
Z? How much?
2, sir.
Oh, I actually have not computed that one. So I mean, you can just compute it.
Sir, like because sir Wi like the value of x1 and x2 will just propagate straightforward without being multiplied or added by any other term.
Right. I think all the activation values of every layer will be 1, right?
Yes, sir.
Yeah. So all the way it will go down, and then in the Z, what are you getting?
2 for the first ID.
Okay, you are getting the value 2 in Z.
Sir, I think it will be
Yes.
1.
Yeah, I just want to know, like, yeah, I'm not giving my own opinion, but if anybody else is doing that, we can then cross verify. Any response from anybody?
So the final output is classification, right? Like it should be
Yeah,
one or
it's a classification, yeah, because if you look at the level, it's a binary classification task.
So could you repeat what is F?
F, you mean the activation function?
Yes, sir.
Oh, it's a ReLU.
So for the last layer as well.
For the last layer, you can take ReLU, yeah.
So then output should be 1, I think, Z.
The output should be 2 in that case, right?
So but ReLU for greater than 1 will become 1, right?
Yeah, absolutely. Anything greater than equals to 0, the value will be written in ReLU. Else it is, if it is negative, it is 0 then. Yeah.
So Z
So,
would be 2, I think.
so the neurons are numbered from top to bottom. Okay. So the topmost neuron is numbered 1, and then gradually you go down. So if you look at that, then okay, so you are still sticking to your initial answer that the Z value will be 2?
Sir,
Yes,
I
sir.
think it will be 1 because
Yes, sir.
W511 will be 1, but W5 21 would be 0. So,
Right, right, because it will be 1, yes, that's correct. So only the link corresponding to layer number 5 1 neuron to the last neuron is basically 1. Okay, the way we have initialized these parameters. Okay, so that is the thing that. Uh, okay,
Excuse me,
so
sir. I have a doubt in this.
you have a doubt?
Yes, sir. Like, sir, ReLU function is basically x comma max of x comma 0, right? So, like in the sixth layer, we would get like 1 from the upper layer and 1 from the lower layer. So when we add both of them, it should be 2 comma like max of 2 comma 0. So ideally, output should be 2. So why we got it as 1?
Sir, in sixth layer, there should be sigmoid function rather than ReLU, I think.
Sorry.
Sir, in sixth layer, there should be sigmoid function for
No, no,
classification.
you can take sigmoid or anything else, but just for simplifying this one, it doesn't really matter. Like at least for derivation, doesn't really matter. So, but yeah, you can take sigmoid, ReLU, whatever. But I'm just asking you to do it for sigma ReLU because just to simplification, you can simplify the computation.
Okay,
That's
sir.
it.
So sir, like we can use ReLU function for classification problems as well.
ReLU for what?
Like here our output, like desired output, is basically a classification, like problem based on classification.
Yeah.
Like can we use ReLU for classification problems? That's my doubt.
You could use ReLU for classification problem. But people, that is non-standard. Generally, what happens is that in the last layer you took softmax kind of thing and then basically convert the whole thing. Yeah, but in this case, I mean, what my objective is to make sure that you can do the backprop correctly. So whether you take ReLU or Sigma or something else, that is I don't think that's a challenging thing to do, right? So you just take for simplicity ReLU here. But forward pass is all right. But my main intention that whether you can compute daily del W113. Okay, but that's the main thing that you have to do in back propagation, right? So that's the thing that I'm interested in. But I believe the value of Z will be 1 when you take the forward pass for the sample ID 1. Okay, is anybody contesting on that? Anybody find anything, any problem with that?
Yes, sir. I still think it should be 2.
Should be 2?
Yes, sir. I doubt. Like I think it should be 2 because we are using ReLU, so it should be the max of x comma 0, and here like the value of our x would be the.
Okay,
like,
so what is the input received by say neuron in 6th layer?
Sir, one from the upper side and one from the down side.
How one from the downside?
It is 0 from the down.
Because the weight that you have from 2 to the last layer, last neuron, is basically that's a 0 weight.
Okay, sir, got that.
It is
Yeah,
because
yeah,
we initialize this weight in that way, right? So that is why I'm saying this is 1. So somebody
Yes,
who told 1, he is correct.
got
Okay.
that. Thank you.
So you have this activation, all right. Now you do the back propagation and figure out this value daily del W311. Okay, now before you move on, I want to know so del E del W311, it is basically here in this particular weight, right? So this particular weight, right?
Yes.
Yeah, okay. Now in order to compute that, what you need to do first?
Sir, firstly we'll calculate the loss, I think.
Yeah. So loss you already, because once you took the forward pass, you know the Z, and then you also have the level, so you can very easily compute the loss. For example, if you take the squared loss, you can very easily compute the loss. Okay, so that's not something that is extremely challenging. But in order to compute daily del W311, what next you have to do?
So we have to identify the weights which it will affect in while going forward.
Try to what?
We have to find the weights which it will affect if the W311 is changed. Then which other?
No, you have to compute the derivative, no? Daily del W311. So how do you compute that?
So we'll first compute del by del W213, del W115, and del by del W215. Like, sir, now we'll do the backward pass.
Right. So first you have to compute these numbers, okay, for all the weights, for example, associated with say layer 5 to layer 6. Okay. So W512, W521, sorry, W511 and W521, and then bias for 6th layer. So you have to compute all these partial derivatives. Then you come back, okay, connecting layer 4 to 5, you compute that, and then you only compute this daily del W113. So precisely what are the quantities they needed to compute? If you go back to my this formulation, what is the quantities that you need to compute? So you remember that the delta Li is basically a quantity, in a sense derivative associated with each of these neurons. Okay, that's what basically we computed. Now we all know that delta Li will depend on delta L plus I on the other neurons in the next layer. Okay. So that is why basically you have to compute all this. So what are these quantities in this case? In terms of delta, we need to compute. You let me know that, and then I think things will be very straightforward. Okay. So what deltas I need to compute? And which sequence? You tell me the sequence in which I have to compute these deltas. The first which delta I need to compute? You tell me that.
So Delhi by del I1 4, I think.
Daily del.
Maybe
Delhi by del I1 layer.
Sir, I think it should be the last layer.
Yeah, because
Delta
first you
5.
need to compute. So you are doing backpropagation. You say, I already told you that if you look at this formula, okay, very carefully, what is happening? So when you are computing this one, okay, which is associated with the LR layer, okay, in order to compute this delta, you need values from the L plus 1th layer, right? This one, L plus 1th layer. They are dependent on that. They are dependent on that. So as a result, basically, and again, if I compute delta L plus 1, then I need the values from delta L plus 2 and so on and so forth. Okay. So therefore, what we need to do during computation, we basically start from the backward direction. First, we have to do for the 6th layer, then the 5th layer, then the 4th layer. And only then you can compute del E, del B, del E, del W 311. Okay.
Yes, sir. So we
So
start with del 6
in
1.
terms of delta, first of all, in terms of delta, what are the things we need to compute? First, in which sequence? You tell me that. So first, which delta I need to compute?
Delta 6 1.
Exactly. So first, I need to compute delta 6 1. Okay. So first, delta 6 1. Okay. Then what?
Then delta 5 1 and delta 5 2.
Then I have to compute what? Delta
1
5 1
And 5
delta
2.
delta 5 2.
5 2. Right?
Yes.
Then what?
Then delta 4 1.
4 1 and
So
4 2.
basically, I need to compute delta 4 1. Do I need to compute anything else in order to compute this derivative?
No, sir. Delta 4
No,
1
sir.
will give.
No, sir.
Okay, all right. Okay. Now, in order to compute these deltas, any delta, for example, in order to compute delta 6 1, this one, what are the quantities I need?
Predicted output and real output.
Predicted output and real output. What else?
I61.
Yeah, the activation value from this, right? I think which is essentially the actual this predicted output, I believe. Okay, all right. That's actually trivial, but anyway. So in order to compute this one, what I need? What are the quantities I need?
Delta 6 1 and
Delta 6 1 and f dash of I51.
That's right. And in order to compute this one, what are the things I need?
Delta 5 1 and W.
Delta 5 1, delta 5 2, and W's of
W
4.
1 1 comma 3 4 4 4 4.
W4s.
Okay, now in order to compute all these things, whether all these variables and things and materials are readily available to you, that's my question. Or anything you need to compute further. So first you are taking the forward pass. During forward pass, you are basically computing all the activation values. So all activation values are known to you, right? Okay. So all the inputs and outputs actually from all the neurons when you are taking the forward pass for a particular sample, all the inputs and outputs are known to you for all layers. Is this something that I can claim?
Yes, sir.
Okay,
Yes, sir.
all right. So you know all these inputs and outputs. Now, because you know all these inputs and outputs, you also have this the derivative of this deactivation values. That's also available to you, right?
Yes.
All right. Now, because you have all these things, you can compute different deltas. Okay, very easily. Because essentially the delta of 6th layer will depend on the output, delta of 5th layer will depend on the delta from the 6th layer and the output, and so on and so forth. So everything is available to you. Once you compute delta 6.1, then you can very easily compute delta 5.1 and delta 5.2 because everything is available to you. Okay. Then once you have that, you can compute delta 4.1 as well using these delta values of delta 5.1, delta 5.2 and these activation values and the derivatives and so on. Does this make sense?
Yes, sir.
It's just a tabular computation. You start from the right side, just tabular way you compute it. But first you compute all these deltas and then simply go and plug into this to find out these values. So I suggest you to work out maybe with this small example, you can try to work out. Okay, it's a very simple algorithm. It is nothing complicated in it. Okay.
Sir,
Yeah, go ahead.
so delta 6.1 would be just d by dz, right?
Delta 6.1 would be, yeah, it's an error. So it's basically you have this error, which is z minus half of z minus y whole square, the derivative, and then what? So essentially, so E depends on what? E depends on z, okay, and z depends on what? Z depends on I 6.1, right? So our expression for delta 6.1 is basically delta E, and then it is basically delta I6.1, right? That was our definition of delta. Yeah, so basically, using this influence diagram, you can compute it. Okay.
So everything will be 0, right?
Maybe, I mean, I'm just giving you this example because see, if I give you any arbitrary numbers, then it will be very difficult to compute by hand. Okay. So if I give fraction numbers here and there and so on, then it will be very difficult to manipulate by hand. So I gave this example just to make sure that you know how things are actually working. Okay.
Yes, sir.
Okay. So I suggest you to take a small example, try to work out by hand how things are actually working. That's very, very important. Because I'm going to give you an assignment where you have to basically code it up from scratch. No library, nothing. You have to implement backpropagation from scratch. Okay. All right. So yeah, okay. So let's move on. We discuss other things. Quickly wrap up. Okay. So, all right. So the whole process of training a network is this. Okay. Training means all about finding these weights and biases. So first step I mentioned, initialize these network parameters, then weights and biases. Then you have to choose an optimization method. It could be vanilla stochastic gradient descent, it could be Adam, it could be AdaGrad or whatever. Okay. And because depending upon that, you know, anyway, you have to use a derivative. And the step 3, basically, what you do, you take a forward pass for an input sample, compute the cost function, something that you have done in the previous slide. Cost function, then compute the gradients of the cost with respect to parameters using backpropagation. Then you apply the particular optimization method, vanilla SGD or Adam or AdaGrad or whatever to update these parameters, and then you basically simply repeat again and again. Okay. So that is the whole sort of this process of training a deep neural network. Okay, and repeat the following steps means like typically repeat certain number of times. People call this epoch, means taking the whole pass over the data. Okay, so you can take 100 epochs, 20 epochs, and so on and so forth. Okay, so that is how basically you're going to train. Now, if you look at this carefully, that we already know that how we can compute, take the forward pass, how you can compute the cost function, how you can basically do the backpropagation and then find out these parameter values and so on and so forth. Okay, but the thing that we have not talked so far is the initialization of these network parameters, because I need to start from somewhere. Unless I have some starting values, I cannot do anything. You remember that during stochastic representation or random, we need to have the initial values. So couple of observations. Okay, so this, when you are initializing the parameters, okay, there are few observations, okay, that people actually came up with. That makes, you can do, typically it's a random initialization, but then using some kind of, rule. It is not absolutely random. Okay. So the issues that people identified is that, so if you basically, set to very large values, very large initialization, then you are going to have exploding gradients. Then all the gradients that you're going to compute will be very large. Okay, as a result, you have the exploding gradient problem. Now, on the other hand, if you set the parameter values, all these parameter values initially to very small values, okay, then all these activation values is going to be very small. Okay, so you then going to have these vanishing gradient problems, and this is true for very deep network. Okay, it's more severe for deep network. And so therefore, what we really want to do, we basically want to maintain a balance between these two situations. Okay. So I'm going to talk about two initializations. I'm skipping the mathematical proof behind it. There are lots of lengthy proof. If you are interested, you just ping me on MS Team or on my email. I can take one with you in case you are interested more deeper on mathematics on these things. But quickly, in Xavier initialization, what you do, and it's a layer-wise initialization. So WL, this is shorthand I'm denoting. WL means the weights, parameters associated with layer L to layer L plus 1, all the weights. And BL basically biases of a particular layer. Okay, so biases are all set to 0, and the weights are set based on a normal distribution, the Gaussian distribution that normal distribution with two things. For normal distribution, you have two things: the mean and the variance. So the mean will be 0, and the variance is the one which is basically playing all these things. So variance is basically 1 by n of L minus 1, and this is not a power. So n of L minus 1 is basically the number of neurons in layer L plus 1. That means in the previous layer. Okay. So that is the rule you apply, and as you know that this is the initialization scheme is layer dependent. Okay, you basically you are applying Gaussian distribution, but it depends on the number of neurons in every layer. Okay, so that is the first step that you do. Second, another popular one is called gaming initialization. So very similar approach, slightly different in terms of the normal distribution's variance. Okay, so here WL is equals to normal distribution of 0, 2 by NL. Again, it is not power. So NL means the number of neurons in layer L. Okay, so that is the thing basically we do in initialization, and biases are set to again 0. All these biases. Okay. All right. So now what I would like to discuss quickly, the computing the loss values, and I was actually talking about, I briefly talked about this squared loss, but today I will talk about one of the most important thing called cross entropy loss, which is much more prevalent. Okay. So before I move on, let me just tell you how actually these actual values are actually computed. So here what you have, for example, you have an input data. Say you have an input data here. Okay, so input I denoting as I. Now after this you have an NN network, neural network. Okay, layers. Then what you have here, for example, you have some values here. For simplicity, I'm keeping these things are very small. Okay. Say this is say alpha 1, alpha 2, and alpha 3. Okay, these are all scalar values. Okay. So something like that, it is coming out of your this final neural network. Okay, this is basically unnormalized values. Okay. Then what people do? People apply softmax here. Okay. So you apply softmax here. So after applying softmax, the purpose of softmax essentially to convert these numbers into a probability distribution. Okay. So after getting this one, what you can do is something like this. You are going to get P1, P2, and P3. Okay. So how are you getting this P1? So P1 here, softmax is something like this. So P1 is basically e to the power of alpha 1 divided by summation of I is equals to 1 to 3 e to the power of alpha I. Okay, essentially you are converting a set of real numbers into probability distribution by applying normalized exponential transformation. That's what you do. Okay, so you are going to get that, and so this we call the probability values. Okay, I'm just writing down here. So output probabilities. Okay, so this is called output probabilities. And now from here you can think about, for example, these are the basically classes. So you think about it. Now here I am basically considering three class problem. For example, this is say cat, dog, and bird. Assuming that I am basically trying to classify my input into three categories: cat, dog, and bird. Okay, so this P1 will tell that for this particular input I, my train network, to what extent this is going to give you that the image or that the input I will belong to cat with probability P1. Similarly, the input I will belong to category called dog with probability P2 and P3 and so on. Okay. So this is the given an input. This is the way first you compute. Okay, by taking the forward pass, first you compute this output probabilities. Okay. Now basically I have to compute the error. So this is the predicted probabilities given by my network. And now what I have to do, I have to compute the error with respect to the actual levels that is available in the training data. Okay. And there I am going to use a thing called cross entropy. Okay. Now in order to do that, say for example, so say I giving a particular instance that so for I my actual level, for example, is cat. This is my actual level. Okay, from the training data. Okay. Now I have to compare this predicted probabilities, the output probabilities, with the actual levels that I have, and there I am going to apply cross entropy. So in order to do that, remember that I have to basically three-dimensional vector I am getting, okay, as an output probabilities. So I have to convert these things also in this way. So if it is cat, for example, and the way I am basically organized is the first cell will indicate cat, second is dog, third is bird. So this is the way basically I am representing my network. So for a particular example, if the actual level is cat, then its corresponding this gold standard things will be 1, 0, 0. Okay. If it is dog, say for example, if I is dog, from my actual level, corresponding level will be 0, 1, 0. Or if it is bird, then its corresponding level will be the actual vector will be 0, 0, 1. So in this case, because my actual level is cat, so my actual conversion is just to match the whole thing with this output given by the network is this. Okay. So this is in a sense you can think about the gold standard vector, a gold standard encoding, and this particular encoding is the predicted encoding given by my network. Okay. Now basically I have to compute the loss value, and there I need cross entropy. Okay, you can use anything else, but in this particular example I'm showing cross entropy because this is the most widely used one. So what is the cross entropy? So cross entropy is this. Okay, cross entropy, and which I'm just denoting as CE, is equals to minus, okay, minus, so I would say this is a yi into log of pi, where I is equals to 1 to, I'm just writing the generalized rule. In this case, the value of n will be 3 because I have 3 possible categories. You have n possible categories, then the value of n is n. So what is the log of pi? So pi is basically the same that you have here. Okay, the predicted value. Okay, the predicted probabilities. Now this yi is basically the value coming from the actual level. Okay, so in this case the yi's values will be these vectors. Okay, so here it is 1 0 0 and so on. Okay, something like this. So if I look at this particular example, the example that I'm working out, for example, this the actual level of I is cat. Okay, then you guys let me know what if I expand this whole thing for cat, what will be the values? Okay, what will be the values for I equals to 1?
1 log
P1.
Yeah, this is 1 into log of
P1
P1, right? Then
plus 0 plus 0, like 0
0
and
0.
log of P2
plus 0 into log.
0 into log of P3. Absolutely correct. Okay. So this is the way you compute the final loss for a particular input sample. Loss between what is there in your training data and the probability values given by your network based on a particular configuration of the parameters. And then basically we will try to optimize this loss. Objective of course would be to minimize this loss value. Okay, this minimization problem because this is loss value. Okay. Now,
Excuse me, sir.
yeah, go ahead.
Sir, what if P2 and P3 come or any one of them comes out to be 0?
P21. Oh, okay. That's so in that case you can basically do some kind of check. Okay. If it is 0, then the whole thing will be 0. Log will be undefined, right? That's what you are referring to.
Yes, sir.
Yeah. You just you say that okay, if P2 is greater than equals to, sorry, is equals to 0, then basically you simply set away say log is that is going to be 0. In just a little bit of like trick that you play.
Okay.
Okay.
Sir, this is the loss per only one training example, right?
Yeah. And you take summation over all the training examples. So sum over sum. So this is for one, and then you take another sum over all these examples. Okay.
And sir, also another question, like why is the when we are calculating probabilities, why we are taking powers of E? Like why not alpha j by summation of alpha I?
Oh, summation of alpha j by summation of, or just no E transformation.
Yeah. Why we are not doing that?
Oh, okay. So in that case, like what happens is that, so for example, there are different kinds of activation functions. So for example, if you take real U, some of these alpha values could be 0. Okay.
Okay.
So that might create problem. Okay.
Yes, sir. Got it.
Yeah. So, and even if you use, for example, some of this, say linear activation function, in that case, the alpha values might be negative. So difficult to convert that into probability values. So this is a standard practice. When you have a bunch of real numbers, you want to convert them into probability distribution, you simply apply softmax using exponential function and then normalize it. Okay?
Yes.
So in a way, this P1, this softmax which we are using in exponential form is ensuring that P1, P2, P3 are not zero and it doesn't affect that log zero thing, right, sir?
So for anything, yes, that is correct.
I mean, then we won't have that problem of log zero because if it's in exponential form, it can't be zero.
Right, right. At most, it will be very small. Yeah, that's correct. Okay, so this is the, I believe, the most common loss functions that we use in train modern deep neural networks. Okay, of course, this is for classification problem. Okay, but for regression problem, you have to use the squared loss, mean squared loss, something like that. Okay, so I will stop here. Tomorrow we will do little bit of other things like some regularization things. One of this important called batch normalization, which is perhaps the most important component in modern deep nets. And then I will get into decision tree and followed by Bayesian learning. Okay, but I will request you to at least today sometime you please take this small network that I have that I showed you today. Please take that. Please work out at least for 1 or 2 examples to make sure that at least you know by hand how backpropagation works. Okay, that is important, and that's the kind of the only powerhouse that you have. Okay, you have to understand that.
Okay.
All right. Okay. Thank you.
Thank you, sir.
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 Thank you, sir.
Thank you.